All right. So you see the slides? Okay, good. So we're going to start with support vector machines. Support vector machine is a very direct or straightforward way to do classification. It doesn't have any probability model or basis to build a model or to assume a specific model. It goes into the features directly, like it goes into the input samples that you have and try and separate those samples that you have in the feature space. So it's like a direct approach to classification. So given this example that you guys can see in here, we have a number of data points coded, in two groups, the O's and X's, and we have two features, X1 and X2, and the question in here is, where can we draw a line that will best separate those two classes in the feature space in X1 and X2. Without any assumption in here, we can basically just right away go and draw a line. And there are like multiple options in here. Like there will be different lines that you can draw that separates those two classes. So I'm gonna try and maybe, this line in here. So this line will separate the two classes well. Somebody else might, choose a different line. This one also a line that will separate the two classes. Another one may also, write the line this way. So the multiple lines that you can draw, but support vector machine is about the best line, and the best line that separates those two classes. Probably you can all agree with me that probably this is the best line that separates the two classes. Hold on, let me just change the view a little bit so I can see if anybody has a question. If you have any question, probably it's best if you can raise your hand so I can hear the sound and I can, go and change the view. Because when it's in full screen mode, the presentation, I don't see the list, so I can't tell if you have any question. All right, so why this line is the best line that separates those two classes? Basically the answer in this case, why this is the best line, is because this line has the maximum margin that we can get that best separates the data points in those two classes. So the distance in here, if you think of how far, let me choose a different color, each point from the line, it should be maximum. So for those points that are closest to this line that I just drew in here, those points the distance in here will be maximized, will be the maximum distance. So this is the margin that we have for our line, and the best line is the line that has the maximum margin. So that's why this line in here is a better choice than, for example, this line in here. Okay? Because this line here doesn't have the maximum margin that separates those two lines. So this is SVM. SVM is just, for us, a way to have a line Of course, we need to estimate the coefficients for this line, and this is only in 2D. So that's, when you have just two features, right? So, it's easy to visualize. You can come up with this line. You need to estimate the coefficients for this line that has the maximum margin that separates those two classes. So, we'll try and find in support vector machine, we will try and find a plane that separates the classes in the feature space. In 2D, this plane is just basically a line. In 3D, it's a plane. And in higher dimensions, we can visualize it. We will learn, based on that, so we'll start like with this simple classification with only two features in 2D with line and then a plane. But then we will also see cases when, where we can improve on this basic linear classifier and see how we can include nonlinearity and soften what we mean by separate. So we will talk about what we call soft margins for the SVM, and enlarge the feature space that for the cases where the data is not linearly separable. So we need to go beyond linearity, and we see how this is incorporated in SVM. Now, the plane that we talked about is actually what is referred to in SVM as a hyperplane. And I'm going to need to go into like a little geometry in here to explain what is a hyperplane. The line that I drew in here is, in SVM terminology, is a hyperplane. In 2D, it's just basically a line. If beta is 0, but before, this is the equation of a hyperplane. So this is basically the equation. This is our model in here. It's a linear model, and we set this equation to equal 0. If P is the number of features is equal to 2, then it's a line, and we're kind of all familiar. If we go back to remember linear regression, we remember the equation for it, and we know how we can estimate the coefficients for this line. If beta 0 is 0, that's the intercept. So this hyperplane of this line goes through the origin. And now the main thing for us in here is how we estimate those coefficients, the betas, beta 1 to beta p, to create this hyperplane. And we'll put those betas in a vector. That's the beta vector, and this vector is what we're going to call the normal vector. Now, to see things in picture next, hopefully we'll make it easier to understand what is a hyperplane. So, and also, kind of the terminology in here is specific for SVM. So the blue line in here is a hyperplane. This is the line that SVM is going to create to separate the classes in the feature space of your input samples. So that's our hyperplane, and we see in this figure we have some data points. Some of them on the hyperplane, and we also have other data points out, in different areas in the figure. We have the beta vector in here. That's what we call it, the normal vector. And the normal vector is a vector that is orthogonal to the hyperplane. So, so that's part of the definition in here. The beta vector needs to be orthogonal to the hyperplane. And this is the equation pretty much for the hyperplane. And the equation is set, in this case, to 0. Now, we see for the data points that are on the hyperplane, so for those data points that are on the hyperplane, the equation here will evaluate to 0. In this equation, we have beta 1, we have beta 2, and we have beta 0. So beta 0 is -6, the intercept. Okay, and we assume that the betas are given. So let's assume that we already estimated, or it's given to us, the values for beta 1 and beta 2, by which we can draw this normal vector in here, and which is going to be perpendicular or orthogonal to the blue line. And the sum squares of the beta in here, the components that makes the normal vector, will equal to 1. So this is a unit vector in here. And this is important because the value that the equation will give us will be Euclidean distance. Okay, so for all the points that are on the hyperplane, the equation will evaluate to 0, while for the other points that we have, the projection of those points on the normal vector will give us the distance. In other words, like the evaluation of the equation in here of the hyperplane will give us a value that we can interpret as an Euclidean distance between the hyperplane and this data point. And you see in here, in the case of this point in here, the value is 1.6, while in this point in here, the value is -4. So the distance in here can be positive and can be negative. For the data points that are in this direction, in this area, the equation will evaluate to a positive value, a positive distance, while for the data points that are below the hyperplane, the data points will evaluate to, the equation sort of will evaluate to a negative, which means that's a negative distance from the hyperplane. So this is like pretty much a review of hyperplane, you know, what's the terminology in here that we need to use to understand how SVM classify, or how the classification is done in SVM. Okay, let me see if you have any questions before we move on next. Any questions? All right. So just erase everything. So in SVM, we need to estimate the normal vector. We need to estimate the coefficients, the betas in here, that can create this normal vector, which is going to be orthogonal to the hyperplane. So we don't know, you know, if I will go back to the beginning in here, you know, we don't know the case in here. We don't know what's the best hyperplane that I can draw in here. So, but we can, you know, we know from the input samples that we have using X1 and X2, I know that I can, if I will draw a line in here, I know the projection of those points on this line, okay? And, you know, you can start with an initial guess of beta 1 and beta 2, like an, you know, an estimated value, and based on that, based on your guess of the betas, you can have this normal vector, and the normal vector in here is just our way to create eventually the hyperplane that will separate the two classes. Now, of course, we're not going to be trying different values for betas. We have a way to formulate the problem into an optimization problem that by which we can, you know, maximize the margin rather than just one plane. We can maximize the margin that separates those two classes. So in here, we, you know, at the end of the day, we need to estimate the betas to come up with a line, a hyperplane, where the data points at above this area in here and this area in here, all the points, the projection of those points on the normal vector will be positive value, and all the points below the hyperplane, the projection of those points on the normal vector will be negative. Okay, so so this is how SVM work, and you know how SVM works. pretty much by estimating this line in 2D, which is, a hyperplane in 2D is a line. If we will look at this figure in here, and again in this figure we have like multiple options in the first figure in here. We have like multiple options to draw this line. So, we have this option in here, we have two other options, but then again, the best line that separates the classes is this one, and basically this one because it has the maximum margin between the blue and the pink color coded in here classes. So basically, your function in here, the function f of x will be the linear model, and we will set y in here. We need to code the y, the outcome, into +1 and -1. The choice in here, it's for you what is the positive class and what is the negative classes is on you. It doesn't matter. And basically, the function will evaluate to 0 at the data points that are on the hyperplane. So this is like the definition of the hyperplane, or the separating hyperplane in SVM. And since we are interested in not just the decision boundary, we're interested in the margin itself, that pretty much give us the best separation between the two classes that we see in the figure. Our optimization problem can be formulated in a way, by which we need to estimate the betas that will give us a maximum value for M. So it's a constraint optimization problem, it's beyond the scope of our class to kind of know the math behind or how to solve a convex optimization problem. But just to kind of to tell you a little bit about it, it's all what we care about is providing a maximizing the value M in here. So we need to estimate the values for the betas that will give us a maximum value for M. The constraint in here, this is subject to the summation of the betas squared equal 1 to make this a unit vector. For the norm vector to be a unit vector, by which the evaluation of the equation that we saw at the beginning, the equation of the hyperplane, this evaluation in here, for the data points on the hyperplane will be 0, for others will be a Euclidean distance. And it will be positive if it's above, negative if it's below. So that's why the constraints in here is to make the sum of the beta square equal to 1. Okay, so that's the constraint in here, and then pretty much the y, the outcome in here needs to be coded as +1 and -1 for the two classes that we have. So the problem in here is the optimization problem. We can basically use SVM function in a package in R. It will run this maximal margin, the optimization problem, and it will estimate the betas for us. And remember again, the betas in here will define the normal vector, which is the vector that is perpendicular to the hyperplane, by which the projection of the data points in here will be interpreted as distances from the boundary or the margin of the decision boundary. Now the package in R that will run this optimization problem to estimate the betas, the coefficients in here in the model, is called E1071. So it's a kind of weird name. Anybody knows what does it mean? Let me see the chat. All right. So no questions, I assume.
I don't know where the origin of the E1071 is. I thought it was like a course name, but I wasn't sure.
So it's the lab number, the classroom or the lab number where those programmers
Okay.
use this package. So that's why it was called E1071. Okay, so the problem in here is formulated in a way to provide a maximum margin, and that's why we call the maximum margin classifier. We need to estimate the coefficients in here to give us the maximum distance between those classes. And we're interested in maximizing the distance in here because we believe that the maximum, the value in the training data set, we will be able to generalize better when we have testing set to try out. So that's again the basic idea behind SVM as a maximum margin classifier. We need also to see cases where in the case in here, it's kind of easy to separate the two classes. They are linearly separable. The line in here is just kind of perfect in the middle between them. But what if the data is not linearly separable? You see in here in this case we have color-coded input data, and we have the blue and the pink, and we see there's an overlap. So we see some pink inside, and the question here is like, where can I draw the line that best separates those two classes? And when there is an overlap, as you can see in this figure. So the case in here is it's not linearly separable. So we can just draw a line in here. Well, we will have mistakes or we will create errors. And we need to think of a case in here where even if it's linearly separable, so we see in this case, it's easy to just draw a line to separate those two cases. So this is our hyperplane with a maximum margin. But the addition of just 1 point, so what we did in here in this case, from this figure to this figure, we just added 1 point, one data point in the blue class, and the behavior of this hyperplane is tilted all the way to, from this line, dashed line, to the other solid line in this figure. So the addition of just one input data sample in here drastically changed the behavior of the hyperplane. So that's what we sometimes refer to as a non-robust behavior of a model. What if this data point is noise? What if it's an outlier? So so the case in here is we need a model in here to be robust and to be able to handle cases where where we also have data that is non-linearly separable. So for these cases, we need to kind of soften what we mean by our margin classifier. And by softening the margin, it means that we will allow some points to be inside the margin. So we will allow errors. We can allow errors in this case in the hope that softening the margin here, the hope for it to be able to generalize. So the case in here, if you look at the, let's go to this example in here. So instead of having this, the decision boundary that we have in black, solid black, now I'm writing over it in blue. So this is our decision boundary, and let me change the color a little bit to different. Yeah. So this is the decision boundary, and the points that we have, we are color-coded blue and pink. So pretty much, the original boundary or the original margin in here should not, should have pretty much, will look something like this. Okay, but since we are trying to soften the margin here, we will allow some data points to be inside the margin now. Okay, so now we increase the width of the margin, and we see that we have data points inside the margin now. Those will be misclassified, so those will be errors, because we're just gonna we'll be looking at what's beyond or what's outside this margin. So this is our positive class, this is our negative class, and anything inside the margin will be errors, will be misclassification. So by increasing the margin in here of our hyperplane, we will allow mistakes to happen, we'll allow errors, but the hope in here again is to be able to generalize better for testing. Okay, so again, you see in here we have cases in the second figure in here. We allow the margin to include data points. So 8 in here is from the blue class. It is 11 in here. 11 it's in pink class. So we see in here it's also kind of in the wrong side of the margin and the decision boundary in here. Okay, so we allow those mistakes to happen to pretty much be able to generalize better, and this is the only way we can solve the issue when you have a lot of overlap in your data between the different classes. Okay. So the problem now will be rewritten in a way to allow for errors to happen. So we will add this term in here. So our objective is still to maximize the margin in here M, but we can allow some errors, and we will give ourselves like more of a budget in here on how much you will allow these errors to happen inside your margin, or how much your margin should go wider, or to limit in here how wide the margin will go. So the C in here, our tuning parameter now in SVM is C, and that's short for cost. And pretty much the larger the value of C, the bigger the wider the margin, and the smaller the value, the more restricted the margin will be. So in this figure in here, we have 4 different scenarios where this is the maximum C value that we can have in separating or in making the margin as wide as possible. And we see in this case, they are all errors. They are all misclassification, right? Because they are all inside the margin. So this is the largest C value that you can have. And we see in here the smaller the value of C, limiting the margin in here. So maybe this is a good choice of C, but then it's a tuning parameter. So, and also it's kind of a form of regularization, right? So this is how we avoid overfitting in SVM by controlling the C parameter. And again, like any tuning parameter in any machine learning algorithm, the choice of C, you have to kind of do cross-validation to choose a value for C. Okay, so let me see a question. Somebody raised their hand. Alison? Go ahead if you have a question. So the points.
The question. Can you see your question?
Yes. So the points that are inside the margin, there are.
Sorry, I had my phone muted. So is it true that if they're inside that the margin, then they're not? We don't classify them at all?
No, they are misclassification. So there will be misclassification. So when you calculate your training accuracy, because that's the training samples, those will be errors. So you allow. Go ahead.
So no matter which side of the line they fall on, as long as they're inside that margin, we just say we couldn't make a decision on these points, sort of.
Yes. Yes.
Okay.
Because the classification will be outside the margin. Now it's not just one decision boundary, because the solid line, let me go back and share the slides. So what we see in here, the solid black line is what we call the decision boundary, but the dashed lines are the margin in here. So we need to, kind of think of the whole thing now as our classifier. So all the data points that are in this direction will be of one class, and this is the other class. So this is the positive and this is the negative one. So again, C in here as a regularization parameter, you need cross-validation to pick the best value for C, okay? So you need to try different values for it. Any other question before we move on?
There was which graph you said was the best?
For this specific in the slides, well, I mean, you need to see the training in here, the training accuracy, right? So these are like just possible values for C, going from a large value to a small value, just to show you with an increased value of C, you'll have a wider margin, and the smaller the value of C, the narrower the margin will be. Okay. But then again, you need to do this in cross-validation. So you need to report the cross-validated accuracy of the different C values that you will have, by which you will, determine which C value is the best, that you hope will have, a better accuracy when it comes to testing. The other questions from Nupur, can the boundary and margins only be linear? So this is the case in here, we're still talking about linear classifier. So it's a linear SVM. We will move beyond, of course, linear SVM to nonlinear. So that's the next slide. Exactly, the next one is the case where how we can move beyond linearity in here and provide more different functions than just a linear function. So this doesn't assume any probability. There is no probability model in here. It goes into looking at the data points and in the feature space and try and estimate the coefficients of the normal vector that will have the projections of the data points to this hyperplane. It's because we don't assume anything. We don't assume a specific model. Okay, so it's different than the linear discriminant analysis or logistic regression. It's a totally different method. So this is a case in here where, as you can see, it will be difficult to separate the pink from the blue. A linear line in here is not gonna do any good. Okay, it's not gonna work for us. So linear boundary simply doesn't work in some cases, even if you have a large value of C. So that's the case in here. We have, if I assume this is my decision boundary, and let me increase the value of C to allow misclassification, to generalize better, but in this figure, it's not going to work. So we need to think of another way by which our decision boundary is not just a line, and this goes, pretty much we remember from previous classes when we talked about logistic regression or linear regression. To move beyond the line in here, there are ways by which we expand the feature space by using a polynomial, for example, right? So a polynomial regression is a way to go beyond linearity. And the same principle applies in here where we can enlarge the feature space by adding interactions between features or polynomials. Okay, so the concept in here is similar to how we expand the feature space in logistic regression and linear regression, but in this case, by introducing those transformations or by making transformations. So we fit now a support vector classifier in the enlarged or enhanced feature space, and the decision boundary will be in this case nonlinear. So again, we'll still be using the same equation in here, which is kind of a linear model in the nonlinear in the coefficients. So this is still our equation for our classifier. Okay. So also to explain the idea of the feature expansion in here in general. So if you have just 1D, one dimension, you have X, and you have the data points, the blue and the red, and it's easy to come up with just a point in here in the middle that can separate those, two classes. Okay. Now, if there is an overlap, the second figure in here is the case where you have where the blue now is in the middle, so you can't come up with a point that can, kind of cut in here that will give you the best separation. So to work this out, then you can expand the feature space. So you introduce, besides X, you introduce X squared. And now you have two features rather than just one. And you see in the case in here, we were able to draw a line that separates the two classes by introducing X squared, right? By enlarging the feature space. Now the features, the samples are separable in this enlarged feature space. The same concept in here applies also from 2D to 3D. So if you are unable to separate the classes in the feature space in 2D, you can create a third feature, a third dimension. And this third dimension, so if you have X1 and X2, you can create X1 times X2, or you can try X1 squared or X2 squared. And the hope in here is in this third dimension that you added, the data will be separable, or the input samples that you have will be separable. Okay. So as you can see in here, it was inseparable in 2D, but when we introduce a third dimension to it, we were able to see the separation in here, and we have now a plane. So now instead of a line, because it's in 3D, we make a separation using a plane. So this is our hyperplane that separates in the enlarged feature space. Okay. So we can, again, use the same idea in here. So our equation will be the same equation in here of the linear classifier, and just introduce polynomials. So the case in here is, from 2 variables or 2 features to maybe 9. That's the case if you have a cubic polynomial, or interactions. You can also introduce interactions, and now, things in this enlarged feature space, instead of 2D, now you have 9 dimensions. You can find this decision boundary that will separate those two classes. Okay. Any questions? No questions. Okay. Okay. So now the issue with polynomial is if you guys remember the behavior of polynomials with an increase, if you increase the degree of the polynomial, the behavior, especially at the ends of the polynomial, will not be robust. And the other thing is also the increased computation because you kind of introducing more features, so you will have to do more computation in here. So besides the computation, which we can easily resolve with more processing power, the behavior still the non-robust behavior of polynomials will limit the application of nonlinear SVM. So to work this out, there is a way by which SVM is largely or most commonly used is what we call the kernel trick. Okay, so a kernel in here is just simply a function, and it can be a polynomial function, but it has a better, the behavior of the kernel in here is to enlarge the feature space without the abnormal behavior or the non-robust behavior of polynomial expansions using polynomials, and it will reduce a lot of computational cost. Okay. I see somebody is asking a question. Jose Miguel, is that you? You're asking a question?
No, Newport has a question in chat.
No, it's not two decision boundaries. And the figure in here is just a projection. So I need to mention that, sorry. It's the same, it's a decision boundary, but it's not a line anymore, and we can't visualize it in 9D. But there is a way by which we can project multiple dimensions into 2D. So this is just the projection of 9 dimensions into 2D, and this one should be kind of linked together. Okay, so this again, in a way, this is kind of related. It's the same. It's the same boundary. Okay, but we can use some functions to project high dimensions into 2D. Okay, so I don't know if we will have time to go into the kernel trick. So let me just maybe stop here and see if anybody has a question or anything that you guys want to discuss. How is the experience so far? What do you think, Jose Miguel?
Yeah, it looks like we're running out of time, so we can just finish up next time. Yeah, so are there any questions from the students the last few minutes that we have?
Except the audio and video.
Is it only for Lucy, or are other people also experiencing that? Yeah. Okay, so it looks like for some people, I think it's probably fine from our end as far as recording, because I could hear you, Ashar, fine, and then some other people could too. Yeah. I think the people who were skipping some words and maybe your Wi-Fi. So you may need to see if you can upgrade your internet, especially for the remainder of the semester, given that everything is going online. Yeah, if a low bandwidth, and it looks like you'll need to upgrade your Wi-Fi. Use the gas money that you're saving and put it towards towards your higher speed.
Well, I mean, try and close all if you have your browser open. Try and close all windows, even if you're not.
Another thing that they recommended is to not have your VPN on while we're doing this. So you do not have to have your VPN connected in order to use WebEx, and so that would slow things down as well. So disconnect from VPN if in case that's it. You can unmute yourself if you want to talk right now as well. By the way, don't feel like you can only chat.
Yeah. So if you don't own your your equipment for your internet, you can probably contact your internet provider and ask them to change the channel that you're on for your Wi-Fi, and that can help because everybody is at home right now, and so probably you and all of your neighbors are on the same channel, and that slows down your Wi-Fi a lot at home. And if you own it, then you can see if you can figure out how to do it. I don't know. I had it.
If your download,
do it for me.
Lucy, if your download is 84 megabytes per second, that's pretty good. That's quite good. So you shouldn't have an issue. I don't know if you were connected to VPN, but I would say make sure that you're not connected. Okay, so you're not on VPN. Yeah, I don't know. That'd be something, if you can reach out
to IT.
Reach out to IT to see if you can troubleshoot that with them. For the presentations, we're just going to do it remotely via WebEx. So whenever it's your turn to present, we'll provide you the presenter role.
Mm-hmm. And anyway, it's recorded, so we will have a way by which we can link those recordings to Canvas, where you can guys go and read it, watch it again. What about the finals?
We're not sure yet, so we'll see how things kind of progress and then make a decision a little bit later. Regarding the version other than the browser versions, there is an application, the WebEx app, that you can download to your computer.
Yeah.
And so I'd recommend just downloading the app and then connecting that way instead of doing it just via the browser.
Yeah. You can have it on your phone, I think so, yeah. As an app, mobile app.
Yeah. Okay, so how did you all feel that this worked out? Was it pretty clear? Was it simple enough other than this connection issue of some words dropping out?
I thought it was fine.
Okay.
You can hear me.
Yeah.
There was a question about for the data for the COVID problem. Can we predict about death?
Yeah, you can. It doesn't have to be a prediction problem. It can be a prediction, or it can be just visualization. So whatever y'all choose to do.
Yeah.
For the date, we haven't discussed that yet, but probably towards, there isn't that much time left in this semester, so probably towards the end of sometime next month, but we haven't decided yet, so we'll discuss that.
All right.
Okay. All right. Thanks, guys, and stay safe.
Yeah.
And anything that we can do to help, let us know.
Yeah. Don't go anywhere. Stay home. All right. See you guys next time. Bye bye.
Bye.